Good morning, students. Today I am going to discuss about application of van der Waals equation in explaining real gas behavior. Deviation of real gases from ideal behavior at different pressures and temperatures as shown in figure. Some of that is the real gases can be explained here their behavior. The graph is plotted compressibility factor against pressure. Here the some gases are like ammonia, methane, carbon monoxide, helium and hydrogen. These gases we are explaining here. This is a gas which is given that is parallel to the x-axis. It is known as that is the ideal gas equation. But as the pressure increase or very low temperature, very low pressure, the negative deviation of that is the sum of the gases will be takes place like ammonia, methane, carbon monoxide, whereas that is hydrogen and helium, they give that is always that is a positive deviation at all temperature and pressures. These are the it is anomalous behavior of that is a hydrogen and helium will be takes place. But other gases, they give that is at lower pressure they give negative deviations, and at higher pressure they give that is a positive deviation from that is a ideal gas behavior. And particular, suppose we say that is all these gases, they became a behavior at very low temperature and high pressure. They behave like a parallel to the x-axis, and they say that is said that they are ideal. This can be explained by using a following factors. The first factor is nothing but when the pressure is not too high, means it is a moderately pressure or very low pressure. At low pressure, when the pressure is not high, the volume Vm will be a sufficiently large, because as the pressure increases, the volume of the gaseous molecules are decreases, or vice versa takes place. Here pressure is low or it is not high, therefore volume ultimately high, therefore the B may be negligible, and Vm will not be negligible. The van der Waals equation of 1 mole of gas can be written as P plus A divided by Vm square into Vm minus B equal to RT. This is called equation number 1. Actually this equation will be comes from that is the van der Waals equation like P plus A divided by V square into V minus B equal to RT, where we are taking that is here considering at high pressure the volume will replace by that is V is replaced by Vm, and therefore that equation is becomes like a first equation P plus A divided by Vm square into Vm minus B equal to RT. This is called equation number 1. Now when we are saying that is B is ignored or that is negligible, and this is the very small compared to that is V, and that can be negligible, therefore in this first equation you have to put that is B is neglected or 0, then first equation it becomes that is P plus A divided by Vm square into Vm equal to RT. This also can be written as, that is after multiplying this, what happened here, after multiplying this Pm, that is Pvm plus A divided by Vm equal to RT. This can be rearrangement by transferring this value that to that side, therefore Pvm equal to RT minus A divided by Vm. Thus the product of Pvm is less than the RT by the amount of equal to A divided by Vm. As pressure increases, Vm decreases. A divided by Vm increased, and therefore Pvm became smaller and smaller. This explains the deep in the isotherms of the most of the gases as shown in figure of carbon dioxide, methane, whatever may be, ammonia also. These are the giving here. That is a negative deviation will be takes place here, right? Low pressure, that will be a takes place here, that is a negative deviation, because the PV is equal to lesser than that is RT. And this is the one case. And second case, when the pressure is too high. What happen when the pressure is considerably high? The volume Vm will be quite small because pressure is inversely proportional to volume. Volume is high, the volume that is the pressure is high, volume will be decreases, and hence it is says that is small. Now it may not be possible to ignore B. Therefore, the Vm will be negligible, and that is here. Now B cannot be negligible, but P is quite high. The pressure factor, that is A divided by Vm square, may become a negligible in comparison with the pressure, and therefore this equation 1 is replaced by, that is we can reduce what is that, A divided by Vm is negligible compared to, that is a pressure. Pressure is, that is a high, too high, and this value will be a volume will be very low, and this will be a negligible, and from that we can say that is A divided by Vm square is negligible, or it is taken as 0, and therefore equation 1 becomes P plus 0 into Vm minus B, that it written here P into Vm minus B equal to RT. This can be also written as by multiplying, that is PVM equal to RT plus RB. Call equation number 3. Thus, the PVM is the greater than, that is RT, by the amount of equal to PB. As the pressure increases, the product PB increases, and therefore PVM also increases. PVM means, that is a factor, that is nothing but that is a compressibility factor increases. This explains why the PVM after that is reaching minimum and increases with further increase of the pressure as shown in figure. In the diagram we say that is as the pressure increases, the PVM that will be became a greater, and it gives that is a positive deviation, or it be greater than, that is the ideal gas equation. If it is a lesser, at low pressure it became a negative value. Negative means PVM will be lesser than, that is PV is equal to nRT, whereas at high pressure the PVM is equal to greater than, that is RT, and therefore it gives, that is a positive deviation in the graph. Then it is evident from, that is above discussion, that ordinary temperature, while the fact of the term AVM is predominant at low pressure. This is the give, that is at very low pressure it work as, that is it is a main factor A divided by Vm square. That PB is predominant high at the some intermediate range pressure. Therefore, two that is effects balance each other. In this range of the pressure, the gas shows ideal behavior. This explains the existence of the small horizontal portion in the isotherms of gases like carbon monoxide, methane, etc. When the temperature is high, what happen here? When the temperature is high, now we are explained about, that is pressure in the form of pressure. Now come to, that is at what temperature? If the temperature is high, if the given pressure, if at the given pressure the temperature is considerably high, the volume will become a sufficiently large to become a value of A divided by Vm is negligible small. We know that as the temperature increases, volume of the gas will be increased, because the volume is directly proportional to, that is a temperature. At high temperature, the B may also be negligible, because the volume is increases high, and B may be negligible in comparison of Vm, and this is now sufficiently large. Under this condition, the van der Waals equation approaches the ideal gas equation. PV is equal to RT. This shows that deviation becomes less at high temperature, because therefore when B is negligible, then it became a PVM is equal to RT, and that at very that is we say that is high temperature, we say that is it is negligible. Then this graph shows that is compressibility factor against, that is effect of temperature on deviation of nitrogen gas from the ideal behavior. At different temperature, we say that is these are the gives. At a lower temperature, very low temperature, minus 70 degree, it most deviation will be takes place. At that is atmospheric pressure, lower atmospheric pressure, this temperature will be there. Again at this will be a curve will be takes place at 25 degrees Celsius, somewhat less deviate, less value, that is the PV is equal to less value, and this is the again somewhat more value compared to that is at 20 degrees Celsius, and that is a 50 degrees Celsius. It is normally at high temperature, the gas will be remains like a ideal behavior, as this is the explained. Now coming to that is the exceptions. Why the at all temperature and all pressure the hydrogen and helium gas always give that is the positive deviation, means PVM is equal to greater than, compressibility factor is greater than 1 or greater than 0, and it is above that is parallel to the x-axis of the ideal gas equation. Therefore exceptional case, or that is anomalous behavior, or that is it say that is these gases are exception, or some that is different properties are there. How that is explained? Since both hydrogen and helium have a comparatively small masses, because the main factor is nothing but they are small masses, the attractive force between their molecules are too small, because the molecular mass will be less, the number of molecules will be less, and therefore attractive force will be less. In other words, the correction term A divided by Vm due to Vm square due to the attraction factor remains negligible at ordinary temperature. Thus, PVM equal to RT plus PB, that is this call equation number 4. This explains why there is a continuous increase in PVM with increase of pressure in case of these two gases at ordinary temperature. Even though ordinary temperature the pressure increases, it always gives that is a positive deviation rather than that is a negative deviation of the from the ideal behavior, because we see here just in this diagram here the hydrogen and helium, these are always as the pressure increases they will be always give that is a positive deviation, means it is above that is the ideal gas curve, ideal gas equation curve will be there here parallel, but the none of that is the below comes, and therefore this is the exceptional case of that is hydrogen and helium. This explains the continuous that is here. As seen from that is the above discussion, the van der Waals equation fairly satisfies the behavior of the real gases. The temperature at which the real gas obeys the Boyle's law, known as Boyle's temperature. At that temperature, no, when a particular gas it becomes a ideal, and that temperature is called as that is a Boyle's temperature, the temperature at which real gas obeys the Boyle's law, and that is called as Boyle's temperature. That can be given by TB equal to A divided by BR. Here A and B are there is a van der Waals constant, and R is nothing but real gas constant, and TB is nothing but Boyle's temperature. And this is explain about that is application of real gases from ideal behavior. Now coming to that is the critical phenomena. Now critical phenomena is another concept to explain here. Critical means here critical solution temperature whatever may be, that can be explained here. The most characteristic, this is the critical phenomena or critical property, is the most characteristic property of gases is that their molecules lie far apart from one another and are in continuous and random motion. Each molecule therefore leads almost an independent existence. This is particularly so when the temperature is high and pressure is low. However, as the temperature of the gas is lowered, the kinetic energy of the molecule decreases. The volume occupied by the gas also decreases. At sufficiently low temperature, some of the slow moving molecules cannot resist the force of attraction, and they come closer and closer, and ultimately the gas charges that is a gas changes into a liquid state. This liquefaction of the gas result from the decrease in temperature. What it means say that this I have read no, that is simply here no, in the high temperature the all gaseous molecules in the remains gaseous state. As the temperature decreases, the molecules, that is the attractive force between the molecules, will be removed, and hence the all molecules come closer, and a particular temperature the all molecules join together and it became a converted gaseous molecule converted into liquid state. Therefore, at that particular temperature called, that is a critical temperature. Therefore, we say that at particular temperature, above that temperature, the gases remains in gaseous state, but below that temperature, the gases became always in liquid state. The liquefaction of liquid state, and such that is conversion of at particular temperature, the conversion of gases molecule into liquid state, they are called as liquefaction of the gases. Liquefaction means making the gases molecule into liquid form by lowering the temperature. A gas can be liquefied by lowering the temperature and increasing the pressure. As the pressure increases, suppose here two factors are there. One is temperature. We are removing the temperature, or cooling means the attractive force between, that is our kinetic energy of the molecule decrease. Pressure means applying the pressure means the molecules are away from each other. No, they come that is allowed to come near by applying the pressure. Therefore, we say that at lower temperature, the gas molecules lost kinetic energy. The slow moving molecules then aggregate due to attractions between them and are converted into liquid. The same effect is produced by the increase of pressure. The gas molecules come closer by comparison and coalesce. Coalesce means just that is combining to form a liquid. Now coming to this can be explained by using a Andrews. Andrews studied the P and T, means pressure and temperature condition for the liquefaction of the several gases. He established that for every gas there is a temperature below which the gas can be liquefied, and above the gas defies the liquefaction. Means at particular temperature above which the gases always remains gases, it cannot be liquefied, and below that temperature the all gases molecules became a liquid state, and the temperature will be, it is a junction exactly. It maybe became a, above that temperature it became a gases, and below that temperature it became a liquid state, and such state is called as a critical that is a temperature. This temperature is called as a critical temperature of the gases. The critical temperature of the gases may be defined as the temperature may be defined as, what is that? Defined as the temperature above which gas cannot be liquefied no matter how great pressure is applied. Means at a particular temperature above that the gas cannot be became a liquefied. They are remains liquid state, and no matter how the pressure, how great pressure, even though applying the high pressure, that above that temperature the gases cannot be became a liquefied or remains the liquid gaseous state, and such temperature is that temperature is called as a critical temperature. For example, the critical temperature of oxygen is minus 118 degrees Celsius, and the hydrogen will be a, that is a minus 240 degrees Celsius. Then similarly we say that is a critical pressure. The critical pressure, the minimum pressure required to liquefy the gas at a critical temperature. Now whatever maybe we say that is at critical temperature means at particular temperature above which the gas cannot be liquefied. And that point, no, that temperature, whatever may be temperature will be a exist, or that is possesses by the gas molecule, that is called as a critical pressure. What is mean by critical pressure? Means the minimum pressure required to liquefy the gas at critical temperature is called, that is a critical pressure. For example, the sulfur dioxide can be liquefied at minus 8 degrees Celsius if the pressure is 1 atmosphere. But it can be liquefied even at higher temperature 20 degrees Celsius if the pressure is increased, that is a 3.24 atmospheric. The critical temperature of oxygen is 118 degrees Celsius, and that hydrogen is minus 248. It is a range of them, because even though critical temperature we are applying, that is a particular temperature, no pressure increases, even though that became a not liquefied, and that is called as a critical temperature. And therefore the critical temperature of the oxygen, that will be changes. This is the critical temperature, and 50 will be a atmospheric pressure, and hydrogen 240 minus 240 degrees Celsius for that is the critical temperature, whereas 18.8 atmospheric pressure will be a that is a critical pressure of that hydrogen gas molecules. Then similarly we say that is critical temperature of the carbon dioxide 31 degrees Celsius, 31.1 degrees Celsius, and critical pressure of the gas will be 72.9 atmosphere. Then similarly we can explain that is a critical temperature and critical pressure. There will be a critical volume. The critical volume of the gas can be explained that the critical volume is volume occupied by the 1 mole of gas at critical temperature and pressure. The volume occupied by the gas at critical temperature and pressure, that is called as a critical volume. They may ask very important, they may ask for what is mean by critical temperature, critical pressure and critical volume means. You have to be able to explain this. For example, critical volumes of the carbon dioxide, oxygen, hydrogen are that is 94.0, 78.2 and 65.5 cubic centimeter per mole, and these are called as these are all are called as critical constants. And so far we have discussed about application of the ideal gas behavior from that is ideal real gas behavior from ideal gas equation, and then we also explain that is a critical phenomena. In next class I have to explain about Andrews isotherm of carbon dioxide. This is the most important point of the examination. Thank you.